Hello and welcome to Nekton Submarine STEM 2020. Wonderful to have you all with us, and I'm very excited by this live lesson that we've got for you today. It is entitled Submarine STEM, and it is all about the science, technology, and engineering involved in exploring the deep ocean. Now, we'll be talking about how do you make one of these. This is the submersible, and also we'll be having a wonderful talk from Patrick, who runs and founded a submersible company, Triton, and they make these amazing machines over in Florida. Now, before we get started, a few things. Big shout out and thank you to Inmarsat for their support of Submarine STEM Live. And also, I think I've just over here, I've just got some shout outs for some of those schools who are watching. So let's see who we have. I think we have Landmark International School, and they've asked to say, please say hello to all the students at Landmark International School, Cambridge, who are following the super week of live learning at home. Well, it's wonderful to have you all with us. So a big wave and shout out to all the students there. We also have Mutt Hill Primary, who are really keen to learn more about our oceans while they're home learning. So we've got loads of oceans content coming up over the next weeks, not just Submarine STEM 2020, but we also have Arctic Live in a few weeks' time as well. And I've heard rumors that we're putting on a Coral Easter holiday science club online, but more confirmation on that very, very shortly. And then a massive shout out also to the students and pupils and homeschoolers and families and parents and carers, as we all are now, to E.T. Booth Middle School. So a big shout out to everyone there. And indeed to all the families and students who are watching. So we have registered, and I don't know whether we have that live as well, we have registered students from the USA, the UK, Indonesia, Bermuda and Australia. And I'm delighted to say that we are just connecting live to Patrick over in Florida. Wonderful to have you with us, Patrick.
Thank you. Yeah, good to be here.
And you're going to be talking to us about that very simple task of building a submersible that will get us to the deepest point on the planet. Have I got that right?
That is correct.
Well, it's fantastic to have you with us. So without further ado, I'm going to pass it over to you. So I think we've got a wonderful sort of 15, 20-minute talk from yourself, and then we're back to Q&As. So please do put your questions on the live chat on YouTube. Remember, if you are under 13, that should be through a parent or responsible adult's account. If you need any help, our teacher moderators are online, both on the live chat from our website and on YouTube itself. So pop any questions, tech, submarine, or otherwise there. So I'm just think we're just getting ready with all the AV and everything else set up. Wonderful Ellie, who's our live producer today. And I think we're ready to roll, Patrick. So over to you.
Okay, well, thanks very much, Jamie. I appreciate that. And Ellie, I appreciate you guys organizing this event. And I'm very delighted to have an opportunity to speak to your students about my great passion, which is the ocean. My name's Patrick Lahey. I'm the president and co-founder of Triton Submarines, a company that's been manufacturing submersibles for private yacht owners since 2006, when we began doing that. Before we get started today, though, I want to take a moment to acknowledge the incredible and heroic efforts of these two gentlemen. To the left, you've got Dr. Don Walsh. To the right, you've got Jacques Picard. These two brave individuals made a dive, an historic dive in 1960, in January the 23rd, to the bottom of the Challenger Deep in a craft that was quite different from the one that we manufactured. I have the good fortune of knowing the gentleman on the left, Dr. Walsh, And he actually accompanied us when we made our trip to the Challenger Deep in the spring of 2019. And it was a great privilege and honor for me. Don asked if I would wear the very same watch that he had on his dive on my dive, which I happily did. He said it got him there safely and back again, and it did the same for me. So with that being said, we'll move on. Great quote here from Dr. Don Walsh. Fright saps your mental acuity. Look at that craft that they dived in. The Trieste was a massive vehicle, 150 tons. That tank that you're looking at was filled with aviation fuel. They vented the fuel off into the atmosphere, into the water to make the vehicle heavier. And then they jettisoned steel shot out of hoppers that were located underneath the vehicle to make the submarine lighter. We fortunately have moved the technology down the field, and we have the benefit of using quite different systems and technologies today in our bid to get to the bottom of the ocean. I want to start by just giving you a quick background on myself. I grew up in Ottawa, Canada, about as far away from the ocean as a person could be. I didn't see the ocean until I had the good fortune to move to Barbados at the age of 7. My dad was building houses down there, and that's really when my love affair of the ocean began, and that love affair continues to this day. I know without question this view that picture that you're looking at, which was the view from my backyard as a kid, had profound impact on me, and certainly I would say accounts for the direction I chose in my life. When I was 13, I learned how to scuba dive. At the age of 19, I became a professional diver and began working in the offshore oil and gas industry. In the early parts of my career, I was lucky enough to work for a company in California called IUC that had a number of submersibles, human-occupied vehicles. And after I made my first dive in one of them, I was hooked for life. And here it is, sort of 27 years later, and I'm still playing around with them. And I still feel privileged and very fortunate to get to dive in these incredible machines that take you to places you could simply not see without them. I'm going to show you a quick 1-minute video clip about Triton Submarines. Rather than go through our company history, I thought this 1-minute video does a pretty good job of summarizing it all in a punchy and hopefully interesting 1-minute video. Here you go.
'Into Great Barrier Reef again. I mean, I was in a very, very remarkable research subject. It was just unbelievable. We need to get hundreds of these. We need to get on board it. 14,000 people.
Officially trumps anything I've done in my entire life, personal and professional.
There you go, a shameless plug there for my company, Triton Submarines. But in all seriousness, one of the reasons I like to include that little video is that you see the people who dive in these subs and the impact that a dive in a submersible has on an individual. It's a visceral experience. It connects you physically to the things that you're seeing. And as I mentioned a few moments ago, it allows you to go to places and to see things you simply couldn't see any other way. So submersibles are wonderful machines, and I am very fortunate to have a company that gets to create these great, fantastic things. And to that end, this presentation today is not going to be focused on our normal products, but instead on a very specific sub that we developed over the course of about 4.5 years for a very specific individual. And that individual is standing right there to my right. His name is Victor Vescovo. Victor is one of these sort of hyperachievers. I refer to him as a serial expeditionist because he's a guy that just never seems content to rest on his laurels. He's always looking for the next great challenge. And Victor and I became acquainted, or Triton, Victor and I became acquainted in 2015. Victor had summited the tallest peak on each of the 7 continents. He'd skied to the North Pole and the South Pole. And now he was looking for a new challenge. And this challenge was he wanted to dive to the deepest point in each of the 5 oceans. And he was wondering and asked Triton if we could build him a machine that would allow him to achieve that goal. Of course, we said yes, even before we knew we could do it. We'd been actually thinking about the idea of building a full ocean depth submersible for some time, and Victor provided us with the opportunity. And for that, I will always be deeply grateful to Victor. You know, it does take people like him, mavericks, people who are willing to challenge conventional thinking and give small companies like ours an opportunity to produce a revolutionary new craft. And so today's presentation will be focused on the submersible that we developed for Victor, which we call the Triton 36002, or the full ocean depth Triton. And this is what we needed in order to achieve his goal. We needed to create a submersible. We needed to identify a ship, build landers, which we use for navigation. We needed a mapping system to be able to map these areas of the trenches. And then we need, of course, assemble a great team. And Victor, of course, had to provide tremendous resources to us. It was a very expensive undertaking. As I said, the undertaking required 4.5 years of our lives, those of us who were involved in it. So it was not a trivial thing, but it was also a great accomplishment. So I think, like in most things with life, the more difficult something is, usually the more rewarding it is when you finally achieve your goal. I'm just going to walk you through how the submarine was kind of conceived. When Victor first came to us, he didn't really have a fully formed idea of what he wanted. In fact, what he said to us was, just build me a steel ball that you can lower me down into the bottom of the trench and then pull me back up again. But, you know, from our perspective, that wasn't going to move the needle. It wasn't going to move the ball down the field. What we wanted to do was to produce a vehicle that wouldn't just be confined to allowing Victor to achieve his personal objective of diving to the deepest point in each of the 5 oceans. We wanted to build a sub that others could use. So after his expedition was finished, there would be other people that could use it, other scientists, other explorers, other filmmakers, and so on. So we wanted to build a submarine that would carry 2 people. That was really important to us. And we wanted to build a submarine that was going to be comfortable for 2 people to sit in for extraordinary long periods of time. You know, these dives are often, especially ones into the very, very deepest parts of the Hadal Zone, you're talking about dives that are never less than 12 hours and can often be as long as 14 or 15 hours, depending on how much time you spend on the bottom. So we wanted to build a submarine that would comfortably accommodate 2 people. People would sit upright in a setting that allowed them to be in that position for many hours and to, you know, undertake their exploration. We had to equip the submarine with a life support system. The bottles had to be located inside the vehicle because if you were to put them outside, they'd be crushed by the pressure. We had to provide viewports so you could look out. That was a critically important thing. Again, the idea of building something without windows was contrary to everything that I know about submersibles. Submersibles are visual craft, and the more compelling the visual experience, the more powerful and more memorable the experience. So 3 windows. We had to put the sphere around people so to protect them from the pressure. We used titanium, and we had to make that titanium thick enough to withstand the pressure at 16,000 psi or 1,100 bar. So it's 90 millimeters thick. We needed an entrance hatch for people to climb in and out of the vehicle. The submarine was bolted and clamped together. You saw that, or I'll show you in a minute, a video of the hull being formed into 2 pieces. It's 2 hemispheres with a ring, a mating ring, and it's actually bolted together. You can see the 3 windows. What you can't see is you've got the hatch at the top, and then there's 2 penetrator plates on the back. So there's actually 6 apertures or openings in the sphere. It's pretty comfortable, you know, at 1,500 millimeters in inside diameter or 59.5 inches. It's a comfortable place for 2 people to sit all day long if necessary while you're doing your exploration. The submarine had to have a frame so you could hang equipment and be able to pick the submarine up. So there's the lifting system. You can see those are the thrusters that allow us to move forward, backward, up and down, and transversely in the water column. We had to power it with batteries. The batteries sit at the back in bays. There's actually 6 batteries, 3 in each bay, 3 on the port side, 3 on the starboard side. And they're set up in such a way that there's redundancy. If you lose a battery or even a couple of batteries, it doesn't prevent you from continuing your dive. Lots of system redundancy. Because the submarine, you know, because all this equipment is heavy and negatively buoyant, we had to create displacement. We had to create buoyancy. Instead of using the big tank of fuel like the Trieste did, we used this material called syntactic foam. Syntactic foam are glass microspheres in an epoxy matrix that can withstand the crushing pressure at full ocean depth, but provides displacement so that all this equipment that we're putting together will float. In the end, we ended up with over 5 cubic meters of syntactic foam, which is almost 50% of the vehicle's overall displacement. You can see the syntactic foam is carefully arranged in a way that the submarine has a hydrodynamic shape. We needed a manipulator arm as well. The other objective is no point in going down to the bottom and just coming back up again. The idea is we want to accomplish meaningful work on the bottom. So that meant we had to have a way to interact with the environment. So we put this manipulator arm on the sub so that we could recover samples and, you know, we could interact with our environment in a meaningful way. The landers that we would deploy were the primary means of collecting those samples. The submarine has to be very heavily ballasted to dive. So you've got all this buoyancy provided by the syntactic foam. Now to counteract that buoyancy, depending on the depth, we need to load it up with these weights. There's twin weights. There's a freeboard and surfacing weight located on the bottom of the vehicle. Those are made up of steel bars. Those steel bars are environmentally innocuous. When you leave them on the bottom, they will decompose. They'll just turn into iron oxide or rust. The only thing that you know, you wouldn't want to be the animal that's underneath it when you release it, because sometimes we're releasing as much as, you know, 600 kilograms of steel on a given dive. Then we had to have a secondary means of adjusting buoyancy. So you've got the main weights that carry the vehicle to the bottom and bring it back to the surface. And then we needed to fine tune the ballast at the bottom using this system of variable ballast tubes. And each one of those tubes contains 8 slugs of 5 kilograms in weight. And the pilot can independently jettison slugs of weight to create neutral buoyancy for the exploration phase of the dive. The whole thing is wrapped up in fairings to keep it nice and streamlined so it can slip through the water at a high speed. The submarine travels through the water column at speeds up to 3 or 3.5 knots, which means we can reach full ocean depth in just over 3 hours. That's a pretty remarkable speed. I know it's not Formula One speed, but it's still pretty fast. In addition to that, when the submarine gets back to the surface, we want it to float, and we want to make it in such a way that the passenger and the pilot can get out. So we added these ballast tanks, which have a self-draining system located on them. And then as well, we needed a trunking for the passenger and the pilot to get in and out of the craft. And when the submarine gets ready to dive, what happens is the pilot will fill the trunking with water, and then that trunking will spill into the tanks. Those will fill with water, and eventually you reach a point of equilibrium and the submarine will dive. When you get back to the surface after jettisoning the weight, the tanks will self-drain. We needed a system for communicating, so we added the modems, which are not only for communication, but also for navigation, as well as a system of being able to identify the submarine on the surface, things like strobes and beacons, iridium beacons that transmit to a satellite. So if the submarine were to surface in an area away from the ship, it transmits to a satellite its position. In addition, we have a sonar, which allows the pilot to be able to see things way beyond your field of view. Of course, when you're on a dive in deep water, there's absolutely no light. So what you can see is limited by the distance that your lights can project. That's only going to be about maybe 10 meters or so, or maybe 15. Beyond that, if you want to see things that are off in the distance and you might want to identify a target, you need sonar. So here's the submarine jettisoning its ballast weights. This is what you would do in order to return to the surface. One of our great concerns as a manufacturer is the possibility that the sub could become entangled on the bottom. So we had to create systems on the vehicle where any source of entanglement, like the thrusters that stick out or the manipulator arm, could be jettisoned by the pilot by pressing a button and breaking a sacrificial bolt. And I'm just going to show you a picture. That's what the arm looks like when you jettison it, if you had to. Of course, you wouldn't want to do that lightly. The manipulator arm is worth about $350,000. The batteries are worth about $750,000 a piece. So you wouldn't jettison these things lightly. But if you did need to jettison them, it's nice to know that you've got a completely redundant system to be able to do that. We can also jettison the thrusters, which are the most likely source of entanglement. And if you did find yourself tied up in a rope or something like that, being able to jettison those thrusters is an important part of being able to return to the surface. The submarine sits in a trolley like this on the deck, which can slide forward and aft. And then that whole thing sits inside of an air-conditioned or climate-controlled hangar. Because, of course, on this expedition, we were working in polar regions, we were working in tropical regions, and those extremes of temperatures meant that we had to be able to put the vehicle into an environment where we could maintain it, even if it was extremely hot outside or bone-chilling cold. There's a couple of graphics there showing the major components. I'll just skip through those because I know we don't have a whole lot of time. And this is a video showing the hull being formed. Okay, we'll skip the video and keep going. I've got another video of the pressure testing. We'll just skip through that. One of our greatest challenges was to develop electronics that could work both on the surface and at full depth, because you can't have implodable volumes. So you can't use the traditional thing of putting your electronics in a bottle that resists the pressure. We had to develop electronics that live in an oil bath that lives at ambient pressure. So whatever the pressure is at full ocean depth, 16,000 PSI, 1100 bar, the electronics had to be able to function at that pressure as well as on the surface. And to give you an idea and to sort of illustrate the kind of pressures we're talking about, because oftentimes, you say a number like pounds per square inch or kilograms per square centimeter bar or whatever, people don't really intuitively understand that. But here's something that most of you will understand. Think of a jumbo jet, which weighs about 750,000 pounds fully fueled. It would take the equivalent of 292 jumbo jets pressing down onto the sphere to create the equivalent pressure at full ocean depth. This is some of the elaborate testing that we had to do in order to create electronics that would work. Even discrete components like resistors, diodes, capacitors behave differently under pressure. So we had to develop electronics that would be equally effective on the surface or at full ocean depth. We also had a great challenge of being able to navigate underwater. So if we want to be able to identify these deep areas in the ocean, one of the things we have to be able to do is navigate to them. So we create a map of the bottom using the multi-beam echo sounder system that's attached to the ship. And then using those maps and the geodetic coordinates, we use the landers and the acoustic modems to navigate the submarine accurately on the bottom. This is a quick little video showing the submarine being assembled after our first sea trials. Now, like anything else, when you do a sea trial, oftentimes you identify deficiencies, weaknesses, problems, faults. And so we spent a couple of weeks after the first sea trial correcting those things. And here we are in the shop, taking the submarine apart and putting it back together. This is our shop right here in Vero Beach or Sebastian, Florida. So I'll just skip through that, but I thought you might find it interesting. We had to identify a ship, and that's the ship that conveyed us around the world. We actually, during the expedition, we traveled 50,000 nautical miles in 10 months. And that's the helical circumnavigation, the route that we followed. We'll come back to that in a minute when we have our Q&A session. There's Victor at the end of the first dives. Great story behind that, but I don't have time to tell it. Maybe I will later. That's what the interior of the submarine looks like. We did some fantastic science along the way. While that might seem like it was an afterthought, it wasn't. It was one of the primary aspects of the mission. And one of the things we wanted to demonstrate is that we hadn't just built an elevator to take people to the bottom. We had built a vehicle that could be used to conduct meaningful and important marine science research on the bottom. Here's an example of a very cool animal that we filmed. Defies any kind of reasonable explanation. And even our scientists were perplexed when they saw it. There's the sub in all its glory, fully completed during a launch sequence. And there's Victor at the time we completed the 5th and final dive. During the time we did the expedition, we mapped over almost 650,000 square kilometers of ocean. We also did 103 lander deployments, collected 40,000 samples and 400,000 samples, I beg your pardon, and we identified 40 new species. There's the team that made it all possible from Triton. I'm super proud of these guys. They are one of the most tenacious, resourceful, and hardworking group of people I've ever had the privilege to work with. I've got a final video I want to show you guys that wraps it all up.
You did a great dive. Thank you very much. I hope so. Go ahead. 5, 4, 3, 2. I tried to find out who the first person to dive to the bottom of 5 oceans was. And then it hit me with the realization of, goodness gracious, no one has actually been to all 5. And what a fun adventure that would be.
You're clear to begin your diving procedure.
The deep ocean is Earth's last frontier.
Heading 230. Surface LF depth 10928 meters. At bottom. Repeat. At bottom. Good. See on the other side. The last of the 5 units. Here we go. 15 meters from bottom. Surface, the LF has landed at bottom. Thank you all. All of you made this happen. You put your mind to it and you get the right people, almost anything is possible.
Okay, thank you. We'll go back to the pictures or to the map.
Patrick, thank you so much. I mean, it's just amazing not only to hear about the engineering sort of problem solving and prowess that went into building this submersible, but also the fact that nobody had ever been or thought it possible to go to the deepest point in each of the ocean basins. I mean, truly incredible. And we've got a lot of good questions, both those pre-submitted and those coming through on the live chat. I really want to get to your Atlantic story that you alluded to just a bit earlier. There's a good story there, but perhaps we'll just pick a couple of questions first for the students watching. And this is from E.T. Booth Middle School. Is what kind of testing do you have to go through before you commit to descending an underwater craft to the deepest point on the planet?
Well, that's actually an excellent question. I'm glad somebody asked it, but it is actually one of the most significant parts of the project. Was that early on we made the decision to build a sub that was fully accredited. That meant it was certified by an independent agency. In this case, it was an agency called DNVGL, Det Norsk Veritas Germanischer Lloyd. And they have very strict guidelines which we have to comply with. And in many cases, we had blown through the rule book because we were building something that had never been built before. The testing requirements were arduous. They were time consuming. They were expensive. And ultimately, I would point to them as being maybe the most significant part of what made this project different from everything that had preceded it. It was very important to us as a manufacturer to build something that was fully accredited, that other people could use. When Victor's finished his expedition, we wanted other people to be able to use this submersible and use it with total confidence, because we wanted to build a submarine that was designed for daily use at any depth, and that had proven itself through an incredibly intense sequence of tests. So every component on that vehicle has been and was thoroughly tested. There's nothing that went into it that wasn't tested before it was used on the craft.
I mean, it sounds like a completely arduous sort of and time-consuming route, but I mean, it's a great legacy that has been left by the Five Deeps expedition, whereby we now have a craft that can explore any point of our ocean, which is absolutely fantastic.
It is, and the thing that we're most proud of is that we built a daily use vehicle that can be used in the most extreme, the most remote, and the least understood parts of our ocean, the Hadal Zone, which lies from 6,000 to 11,000 meters, or 20,000 to 36,000 feet.
Patrick, there's a question through from Landmark International School here in the UK, and they're asking, I mean, you pointed out a few pieces of changing the buoyancy of the submersible. Is that the only way you can control the descent? Do you just sink, essentially?
Yeah, I bristle at the idea of using the word sink. You know, it's sort of counter to everything that we try to think about when we're diving submarines. So we say dive, but yes, you know, the Triton 36002 is a completely unique vehicle in my experience. You know, I've been working with these subs for a very, very long time, but in most cases, you know, you take a submarine down to a given depth, it undergoes some compression, and then there's a resultant loss of displacement or buoyancy, and then you compensate that by pumping off water or dropping weight or whatever. The LF, or the Triton 36002, is quite different. Because of the extreme diving depth, you still get the loss of displacement, you know, associated with increase in pressure. But something that happens, which is interesting, when you go to extreme depths, the specific gravity in the ocean increases. And as the specific gravity increases, that displacement counts for more buoyancy. So as we, you know, paradoxically, the deeper we dive in the Triton 36002, the more weight we have to put onto it. And so one of the reasons you use weight is it allows you to get to great depth quickly and then return from great depth quickly. The idea being to preserve your bottom time and use it as much of that time in the exploration phase of the dive while you're on the bottom as possible. But yeah, carrying weight is the simplest way of doing that. And we, of course, want to use weight that's environmentally innocuous, because we leave that weight behind. So we don't want to leave anything behind that wouldn't naturally decompose.
And you talk about the rate of descent as fast as possible. And I think you mentioned the knots during the talk, but the question through, I think, from Andrew Chisholm, who's wondering how many miles an hour you go, but it's probably knots, because I think that's how we measure speed.
Sure, but there's another term we could use, meters a second. A knot is about a half a meter per second. So we're actually traveling through the water column at about 1.5 meters per second in order to reach the bottom in the 3 hours. You're actually going faster initially, and then of course you slow down as you near the bottom. And then when you leave the bottom, you're going faster initially, and then you slow down as you near the surface.
Amazing. And there's a comment coming through from Ben Kenyon online, who commented that he didn't know that a submersible or submarine can have that shape. I think we're used to sort of submarines from films having a sort of like a sort of torpedo shape, sort of, you know, and certainly the sort of naval submarines like that. But I mean, I've got a picture, I think, one of your submersibles behind me, and then you showed the limiting factor. How can they have these shapes? Why are they these different shapes?
Well, that's obviously somebody who's observant, but the shape, of course, is a case of form following function. One of the reasons that the submarine is shaped the way it is because we want to build something that will travel through the water column quickly in the vertical direction. So what we what we effectively have is if you look at it from the side, is it's an elliptical shape. So it's narrow, it's tall, and it's wide. But in the vertical direction, which is the direction where we travel the greatest distance, it's very efficient. And so that's how it can travel quickly. And that's why it's shaped in this sort of odd way. It may be odd, but it's very effective at what it does.
And then with your sort of the submersibles that you make with that sort of acrylic sort of pressure hull, that sort of like that goldfish bowl, is there a reason for them being shaped like that?
Yes, because what we're trying to do is optimize the outward view. So with the Triton 36002, the viewing area are those three windows that you can see that in the image that's on my screen. Whereas our traditional subs, which feature completely transparent pressure hulls, you want to do everything you can to optimize the outward view. So you put the ballast tanks on either side of the sphere, you shape them to minimize your outward look and your downward look. And you also cluster machinery and equipment behind the passengers, the occupants, and instrumentation as well, so that it doesn't in any way block your view. And by the way, one of the things that we are working on and we hope to one day build would be a full ocean depth submarine equipped with a transparent pressure hull. Imagine how remarkable that would be.
It's truly remarkable. And did I hear word that might involve ground glass?
That's right. Well, what we would use is glass. Glass. I know most people, you sort of think of glass, and you envision that glass that shatters on the kitchen floor, and so you think, "Well, that doesn't seem like a particularly good material for a pressure hull of a submarine." But actually, glass is a fantastic material. It's incredibly strong, much stronger than steel or titanium. And in compression, it's very, very good. It does present certain challenges, and those are the things that we're trying to overcome. But our eventual goal is to build a submarine that can carry not just 2 people, but 3 people in a completely transparent pressure boundary. So you can have the visual experience of some of our shallower diving subs, which use acrylic, but be able to go to any depth in the ocean. So that's the ultimate.
Sorry. I think there's a bit of fascination online. How big do our piggy banks need to be to get some of these craft? I mean, everything from the limiting factor to some of the shallower subs that you've been referring to.
Well, the limiting factor, or the Triton 36002, has a retail price of $31.5 million, so it's not inexpensive. But when you compare that to, say, the offerings of the other deep diving subs around the world, which cost hundreds of millions of dollars because they were built by large organizations, Triton is a fairly small, pretty live, pretty efficient company. And so we're able to do things that maybe bigger organizations can't, because we aren't encumbered by all that corporate inertia. The glass pressure hull equipped full ocean depth sub that would be able to carry 3 people, our target price on that is $37 million. Our other subs, by the way, are a little bit more reasonably priced. They tend to be clustered in the $2 to $5 million range.
So I think, is this one of your 1002s behind me?
That's right. It's $2.3 million, that one.
Okay, I'll just keep it on the picture if that's okay for now, Patrick.
Very good.
Sorry, back to the live chat. Is this question is what is the most amazing thing that this sub has discovered?
Wow, that's a really difficult question to answer, because we discovered so much. As I mentioned, I think during the course of the 10-month expedition, we collected 400,000 samples. We discovered 40 new species. We mapped 650,000 square kilometers of ocean. Very difficult to say what specific thing was the most fascinating to me. I think diving in the Java Trench on these bacterial mats was fascinating. I had the good fortune to be accompanied by Dr. Alan Jameson, who is a world-renowned expert on the Hadal Zone. And Al is a fantastically interesting individual who really knows that part of the world perhaps better than anybody on the planet. What a privilege it was for me to sit next to him and have him as my guide telling me about these incredible things that we were seeing. And you could tell from the excitement in his voice that, this was truly a memorable thing for him as well. Most of his diving has been done using landers. So being able to sit in a submersible and look out and see these things with our own eyes and experiencing them in real time is a powerfully emotive experience. It's something that stays with you. In fact, I'll say that if you go for a dive in a human-occupied vehicle in a submersible and you get a chance to do that, I guarantee you, if you're not an ocean advocate, you will become one.
I mean, can I ask a couple of things there? We've got hadal and bacterial mats, which I think for the uninitiated may be some fairly niche terms. So hadal's beneath 6,000 meters. Is that right?
Correct. The hadal zone of the ocean lies between 6,000 and 11,000 meters, or 20,000 to 36,000 feet. It actually represents a very small part of the ocean, only about 2%. And for the most part, people have been content to sort of write it off. They say, well, it's the last 2%, who cares? But that 2% represents an area about the size of the continental United States. So it's a vast area. And it's a fascinatingly interesting part of the oceans because there are things happening in this deep part of the ocean that we don't fully understand. And we really need to explore these areas to better understand them.
And just on that bacterial mat thing, that I've heard tell of something called chemosynthesis, so that there's how life is able to sort of almost self-generate in the depths of the ocean where there isn't any sunlight, because we normally think that you have to have sunlight for life.
That's exactly right. In fact, I think it was in 1978, interestingly, fairly recent history. I mean, certainly for me, because I'm 57. But no, 1978, I think everybody sort of believed that all life on Earth was photosynthesis based. But, the scientific community was turned on its head when they discovered these hydrothermal vents in the deep ocean. These are animals, colonies of animals that are living, thriving on the chemicals that are coming out of the ocean. And a whole new sort of ecosystem, chemosynthesis, was discovered and really challenged conventional thinking and made it clear that we still had a lot to learn from the deep ocean. Imagine animals that not only live but thrive living off chemicals with absolutely no dependency on sunlight or the sun that we traditionally think is the giver of life for everything on the planet.
I mean, a whole another world. But Patrick, we've got a few quick fire questions here.
Sure.
Maisie would like to know: is the research that these submersibles do just to do with deep sea animals?
Well, no. It's geology, it's marine biology, it's oceanography. So that's the great thing about a sub. You can take a scientist with a particular discipline down. He might be an ichthyologist, he or she might be an ichthyologist. They might be a marine biologist. They might be an expert on archaeology or geology. And we actually were blessed on the Five Deeps expedition of having a remarkable science team that was made up of people from a wide range of scientific disciplines. And each of them have their own sort of specific interests. Some people are interested in the rocks, and the others are interested in the bacteria or the fish. And there's lots to learn.
Brilliant. From Ben, do you have to be super fit to dive a submarine?
Well, not really. That's one of the great things about a submersible is that you're sitting inside of a pressure-resistant structure. You're not exposed to the pressure that's outside of you. You don't have to worry about carrying around a tank. You don't have to worry about bottom times. It's actually a pretty comfortable, pretty relaxing experience. You have to be able to get down the trunking and into the hatch. So, you have to be reasonably agile, but it doesn't require a tremendous level of fitness.
Brilliant. So we've got from Charles and James in England: how long did all 5 dives take? Was it, how long were you at sea for?
Well, actually, the expedition started in August of, it started in December. We originally were going to start it in August, actually started in December when we completed our first dive in the Atlantic in the Puerto Rican Trench. And then we finished in September. of 2019. So it was 10 months from beginning to end. And during that time, we covered 50,000 nautical miles at sea. And we concluded a number of dives, including Victor's 5 deeps during that time.
And unfortunately, the final question that we have time for today is Lila, who would love to know how many submarines or submersibles, Patrick, have you made?
Well, actually, at Triton, we are about to begin our 20th submarine. So it's not a huge number of subs, but the company has been enjoying, and I think the ocean community has been enjoying, a resurgence of interest in these human-occupied vehicles. And I think a lot of that has to do with the fact that yacht owners who have platforms that can support submersibles and they have the wherewithal to be able to afford them are beginning to recognize how powerful they are. Submersibles, when you dive in them, allow you to become a true explorer in the very real sense of the word. Every time you get into one and you dive below 50 meters, you're most likely seeing something someone has never seen before. And I think there's something very exciting about that, very alluring about that. But yeah, 20 so far, but we're hoping to start ramping production up to where we're building 4 to 6 of these things a year. And eventually, you're going to see them all over the place. Like Oliver said, we need an armada of these things out there. We want to help contribute to that armada.
I really hope that vision comes true, Patrick. Just massive hats off to you and all the team at Triton for making this underwater world accessible to more and more people around the world. Thank you also for inspiring our audience with these sort of feats of engineering and giving an insight to our future aquanauts and marine engineers about what they could be getting up to in the future. So massive thank you for that. Thank you also to Inmarsat, who's supporting Nekton Submarine STEM 2020, and to all the team at Nekton as well. We've got 2 more sessions tomorrow on submarine conservation with Shaheen, learning how all the data being collected on this kind of expedition can be used to protect our ocean. So do please tune in for that tomorrow. Until then, it's a huge thank you to all of you watching. Big thank you to Patrick as well. Thank you so much, and goodbye for now. Bye-bye.
Thanks, Jamie. Thanks, Ellie. Thanks, everybody. Bye-bye.